Okay, so welcome everybody. So we will continue in this chapter 2. So we will continue on chapter 2 where we talk about existence of invariant measures. So again, today is our lecture number 5. So remember in chapter 1 we talked about invariant measures, when they exist, what they imply. Like we have the Poincaré recurrence theorem, which is the first implication of the existence of invariant measures. That point they tend to return. We have also the first return map, which is integrable. And also we have seen some ideas on how to find these invariant measures using the Perron-Frobenius operators and some examples. So in this chapter we will prove under what conditions, like we will put some condition on our space, on our dynamical system, so that it has an invariant measure. So so here in this chapter we will take M is a separable metric space. So by separable we mean that there is a dense subset, a countable dense subset. Metric, it means so M, so by this we mean M has a countable dense subset, and this we mean that there exists a metric D to distance between x, y is a metric, is a distance function. Okay, we will also assume that our dynamical system F is continuous. So in the first chapter we were defining general things on just like measurable maps. So this is continuous. So as I sketched last time, to find invariant measures, like to prove under this condition that we have invariant measure, we need to put a topology on our space, which is a weak star topology. So we need to define what it means by measures are nearby. So in the first section, so we say weak star topology. Okay. So for today's lecture, everything that I'm going to do is in the book, so you can also look at it there. So remark, or an observation here. So given a measure mu, so the collection the integral of phi d mu, where phi is continuous bounded function, this collection uniquely determines the measure. Like if you know what this means, you know the measure. So uniquely determines the measure mu. Because you can see that to know the measure of the set, you can apply it to indicator function not being continuous, but you can do an approximation and so on. So this is really what determines the measure, the evaluation on continuous functions. So it makes sense to say that two measures are nearby or are in the same neighborhood if they agree, or they agree in a big set of functions. Like if I say I have 1,000 functions where these two measures, their integral agree, I can think that the measures are nearby. On the set of 1,000 functions, if I add another 1,000, and the function, the two measures, they agree on this set of 2,000 functions, so the two measures are getting closer and closer. So this is a motivation why we define a basis of neighborhood. So definition. So let C, which is phi1, phi n, be a finite family of continuous bounded function. You know, all along here, in many cases, separable could be replaced by compact, okay? Like when we say continuous and bounded, that is redundant when you have compactness. Continuous bounded function. So for epsilon positive, you define V of mu phi epsilon, which is a set of measures nu such that this is a set of measures such that the integral of phi I d mu minus the integral phi I d nu is less than epsilon for I equals 1 n. Okay? So this is our candidate of like a neighborhood of a measure. Okay? And how small this neighborhood is by choosing epsilon smaller and also by choosing, you know, this set of function to be larger. Okay? So first claim or a lemma, the family this family V mu psi epsilon for phi being a finite collection on function, so phi finite collection, finite family of continuous function, and epsilon positive. So this family defines a basis of neighborhood. It defines a basis of neighborhood. So what do you mean by definition of a basis of neighborhood is that if you take two guys, their intersection contains another one of the family, okay? So proof, it's simple. So if you pick, let V mu, let phi1 phi n1 and phi2, which is phi1 phi n2. So this is a collection of continuous bounded functions in epsilon 1, so epsilon 1 and epsilon 2 positive. You want to find phi, a collection, and epsilon such that V mu phi epsilon is a subset of the intersection. Phi1 epsilon 1 intersect with V mu phi2 epsilon 2. So this you can have by just choosing phi as the union of these two collections and epsilon being the minimum of epsilon 1 and epsilon 2. So choose and epsilon being the minimum of epsilon 1, epsilon 2. Okay. So once you have a basis of neighborhood of every point, so I forgot to say define a basis of neighborhood of mu, okay, or around mu. So this is center at a point. I have neighborhood that has smaller and smaller and converging to this. So from this we have the definition of the weak star topology. Weak star topology. I forgot to say that I did not write a notation here. So the space of measures here is denoted by M, okay? M like this. I should have said it somewhere. Let me do it here. Space of Borel measures. Sorry. Remember, we have also M1, which is the space of probability measures. Okay. So the weak star topology is on M, so the weak star topology. So we write as tau star, okay, to define this topology, like the collection of open sets. On M is the topology defined by the basis of neighborhood that is V mu phi epsilon. Like the open sets are all possible combination of these guys. Like you change mu, you change phi, you change epsilon. So those are the open sets in this topology. Okay. Now notation. If we have mu n converges to mu in the weak star topology, we just write like this, mu n is converging to mu. Okay, that's just simple notation.
Professor,
Yeah.
does this topology has anything to do with the weak star topology we see in functional analysis?
Yeah, in some sense, because that's the topology defined by convergence in distributions like functions. So that's similar.
Those things seems to be functional. At first, I thought it had
Yeah, measures, you can see them as functionals. A measure is a functional, like this. A measure is a functional.
Yeah, it is.
Mm-hmm. Yeah, and yeah, it now makes sense to see, like to characterize this convergence using just convergence of integrals. So lemma, we have that mu n converges weak star to mu if and only if the integral of phi d mu n is converging to the integral of phi d mu for all phi that is continuous bounded and bounded. Yeah, the proof of this is also just simple. So if you suppose that you have this, so suppose mu n is converging to mu big star, and choose this collection equals, so pick a function, so let phi be continuous and bounded. Now consider this collection of functions. This is just this guy here, epsilon positive. So for epsilon positive, consider v mu phi. Epsilon is a neighborhood of mu, is a neighborhood of mu. So by this convergence here that exists, so mu n converge star to mu, imply that there exists n naught such that mu n is in v mu phi epsilon for all n bigger than n naught. Okay, just definition of convergence via topology. And yeah, and you translate what this means. This means that IA, so the integral of phi d mu n minus the integral of phi d mu is 3 to less than epsilon for all n bigger than n naught, which is equivalent to saying that, which implies, sorry, that you have convergence as this as numbers. So this is a convergence by numbers. Also, the other way, you can just, if you pick any, yeah, so conversely, if you have that phi d mu n is converging to phi d mu for every phi, so we choose let phi be a collection, phi 1, phi n, so continuous and bounded. So this is true for every phi I, okay? And then you choose for every I, you have an ni, after which, so you choose this and epsilon positive. So for every I equals 1, n, there exists ni such that the integral of phi I d mu n is minus the integral of phi I d mu. This guy is less than epsilon for all n bigger than ni. Basically, what you do now, you just choose I to be the maximum of this ni. It is finite, you know, finitely many i's. So choose n naught to be the maximum of n i's, and you will have that you will have that this implies that mu n is in v mu phi epsilon for all n bigger than n naught, which means convergence. Okay? Okay. Simple. So yeah. So in general, it's a little bit difficult to work with this definition of the topology using these functions, because you're dealing with measures. It makes sense to use, something that, that uses sets. Okay. So we will give an equivalent definition of this topology, which is called the portmanteau theorem 2.2. So this is just a way to rewrite this topology that is, more useful to do calculations using these open sets. So this is about characterization of tau star by sets, okay? So there is this terminology which is used, when you deal with topology. So given two topologies, tau 1 and tau 2, so we say that tau 1 is stronger. We say that tau 1 is stronger or finer. We will also use this terminology. I like better this one, finer, because at least it helps me, have the idea behind this definition. Because finer means that the sets are like finer, are smaller in terms of size. That we say that tau 1 is stronger than tau 2 if every open set in tau 2 is also an open set of tau 1. And we write tau 1 is stronger than tau 2. Okay? Because you can think of having an open set, having a topology which is given by a collection of open sets. You can refine these open sets, get another topology, and that topology will have more open sets than the other one, and open sets here can be written as union of open sets with respect to tau 1. So in this case, we also say that tau 2 is weaker. Tau 2 is weaker or coarser, following this. Coarser than tau 1. Okay, this is not English, so I should say than here. This is not English. It's stronger than, yes. Tau 1. And for this, you write, as you say, tau 2, tau 1. And we say that the two topologies are equivalent if, so we say that tau 1 and tau 2 are equivalent, if are equivalent, we write this tau 1, tau 2. If tau 1 is stronger than tau 2 and tau 2 is stronger than tau 1. Okay, this is just some terminologies. Now we define so let F, which is F1, Fn, be a finite collection of closed set closed set. So tau F, here the subscript F is to mean, I think from the Portuguese, which means fechado, like we use closed subsets and close fechado here. Tau F be the topology defined by the basis of neighborhood. V, F, mu, F, epsilon is a set of nu. The space of measures is that nu of Fi is strictly less than mu of Fi plus epsilon for I equals 1. Here I make this, I said that this is a basis of topology, but you can check it, okay? You can check this defines a basis of topology. Like if you take the intersection of two guys, you can find a smaller one by just choosing F and epsilon. And similarly, if you have A, which is the set of A1, AN, collection of open sets, tau A is the topology defined by basis of neighborhood. V, A, mu, A, epsilon. Nu of AI is greater than mu of AI minus epsilon for I. This is also a basis of neighborhood. It's easy to check. And lastly, we define, so given B, let B be the collection of, oh, I should not write B like this. I should, anyway, B1, B, N. So that BIs are Borel sets with the measure of the boundary of BI is 0. So when a set satisfies this, we say that this set BI is a continuity set of mu. So in this, we say BI is continuity set of mu. Okay. So also there is a topology given by tau c is defined by the basis of neighborhood. What is this? Basis of neighborhood is given by Vc mu b epsilon is the set of nu m such that mu of bi minus nu of bi is less than epsilon for all I equals 1 n. Now the portmanteau theorem tells you that all these topologies are equivalent to the weak star topology. Position the topologies tau star, tau A, tau C, tau F are equivalent. So this is just to say that you can write this. Okay. Okay, so let's prove this. So this is how we will prove it. We will prove that tau star is stronger than tau f, which is so this is easy to see that tau f is equivalent to, which is stronger than tau c, which is stronger than tau star, and you come back to where you started. All right, so let's prove this. Let's prove that tau star is stronger than tau f. What does this mean? This means that if you take an open set here, you want to prove that this is an open set here also. So for this, you take epsilon positive and phi 1, phi n, a collection of continuous bounded functions. And so you want to prove that, and mu also, you take mu, a measure. You want to prove that this guy is an open set. V mu, so want to find what? Oh, I should not choose function. I should choose closed sets. Okay, sorry. F1, Fn. So these are closed sets. And you take a mu measure. So you want to find a collection of function phi, which is phi1, phi n. Okay, not necessarily, but for this proof we will have the same number. And epsilon prime, if possible, if needed, to change epsilon, such that v mu phi epsilon is a subset of v f mu f epsilon prime, sorry. Yeah, so this is what you want to find. And to do this, we're going to use something that is like general. So, so let me define, for delta positive, let f delta, fi delta be the, so I will say what this means, be the delta thickening of fi. By delta thickening, this is what I mean. So this is my set f. I take like delta neighborhood of the boundary here. And this is f delta. You just make f a little bit by going delta distance. To write it formally, so formally you write f delta, fi delta, is the set of x in M such that the distance between x and fi is less or equal than delta. And you know the distance for set to a point is just the infimum, okay? Distance x fi is the infimum of the distance between x, y, where y is in fi. All right, so with this you can construct your functions as follows. So you take a type of, cut of functions. But here we don't have a lot of structure. We just do Lipschitz. So suppose you have your f delta. I will just show you the picture on the real line. So this is your f. F delta is just, you add delta here. So you can find a Lipschitz function phi I such that phi I is identically 1 here in f, and it is 0. Phi I is identically 0 here, and phi I is also identically 0 here, and here it is going from 0 to 1 and Lipschitz. So we can find, this is a type of a bump function or cutoff function. We can find, so if you have more structure, like, because I'm just on a metric space, if it was a smooth differentiable space, I could ask this to be C infinity. We can find phi I such that the support of phi I is in f delta. The support is, the closure of the set of points where it is not 0. And here we can make it Lipschitz, okay? And phi I is fi here is identically 1 in Fi. Yep. So basically, this is just to say that phi is Lipschitz, so i.e. phi I is Lipschitz, and the indicator function of Fi is less or equal to phi I, which is less than the indicator function of Fi delta. So once you have this, you can check that this satisfies. Where is this? Yeah. So you can check that choosing delta equals epsilon over 2 we have that v of mu phi delta or less than the, you can, this is a subset of v of f mu f epsilon. Yeah, so this is easy. And the fact that tau A is equivalent to tau C this is also easy. You just choose, the complement of the set. So if you have F, which is F1, Fn, you can define A to be F complement, which is F1 complement, Fn complement, and you can see that, so these are closed, so these are open, and you can see that VA of mu A epsilon equals V F mu F epsilon. Yep, so this is just nothing to do. Now how to see that tau A or tau F, like any of them, is stronger than tau C. For that, you need to choose open set here and prove that it is open there. So let B open set, you choose, points of sets of continuity, B1, Bn, okay, says that mu, the boundary of Bi is 0, and you want to prove that this is so you want to prove that the neighborhood you get from this is an open set with respect to tau A or tau F, like it's contained in an open set, or contains an open set of these topologies. So to do so, you can just choose F to be the closure of B1, closure of Bn, okay? Now, the measure of the boundary being 0, this guy will imply that the measure of F, so B I bar equals the measure of Bi. Similarly, you could define also the interior of these sets, okay? You could define the interior of those sets as well. Now, Let me refresh a little bit my throws here. Okay. So now you pick an epsilon positive also. So let epsilon positive. So pick nu in VF mu F epsilon. So you want to prove that this is a subset of the neighborhood defined by those set of continuity. Then what do we have? We have that nu of BI is less than mu of BI plus epsilon. That by definition of this. And also, if you see similarly from there, if you also choose you could also see that this guy here is the same as VA of mu A epsilon, where A is just the interior, okay? Where you can see that A is like given by interior of BI's, B1, interior of BN's. Okay? And so this nu would be here, so it would mean that mu of BI will be, yeah, if you combine these two, what you basically have, you will have that nu of BI minus mu of BI is strictly less than epsilon. Because all these sets, they have the same measure, the interior and the closure, they have the same measure because the boundary has zero measure. So this implies that VF is a subset of VC mu B epsilon. Now this part is a little bit more tricky to prove that the continuity, the topology given by the continuity sets is stronger than tau star. This one is a little more delicate here. So to do that, you choose a neighborhood, so let epsilon positive, mu in M, and then you take a collection of functions. Okay, phi n. So you choose a neighborhood here. So we have a neighborhood. This defines V of mu phi epsilon. You want to find a neighborhood in this topology that is contained in that one, okay? So to do that, we write let L be the supremum with I and X of phi and epsilon positive. I have epsilon positive. So we need to find this collection B, B1, Bn with mu of boundary of Bi equals 0 n and that this neighborhood VC mu B, probably epsilon prime, is a subset of V mu. Right? So we start with hope I will get to what I want to do today. I'm sorry, today's lecture is very abstract because it's just dealing with, this topology, which is defined in an abstract way. And yeah. Actually, this chapter is abstract. This is an existence result, so it is just an abstract result. Yep. So see that for every I 1 to n, these guys are pairwise disjoint. Phi I minus 1 of S intersect with phi I minus 1 of S prime is empty for S different than S prime. So this is just because these are functions. These are well-defined functions. Okay? So since these guys are pairwise disjoint, so the measure of these sets has to be 0 except a countable number of them. Because if it is not 0, you will sum them up. If it is not 0 in a continuum, you will sum them and you get something that has infinite measure. Okay? So then there exists at most countably many S in minus LL such that the measure of phi I minus 1 of S what do I want to say? There is uncountably many. So there exists uncountably many. That's what I want to say. Is 0. Okay? Because otherwise you get infinite measure by these guys being disjoint. So for this we can pick some time. So let minus L, which defines as T0, which is less than T1, T2, Tk, which is L, yep. So we have countably, like finitely many of these guys, such that so there is this condition which is Tk minus 1 is less than epsilon. Actually, I can just is this. Okay, let me do this. It's the same. And we define Bij as this set, which is phi j minus 1, phi I minus 1 of Tj minus 1 Tj Oh, I forgot to say that these are chosen so that it is 0, so that this guy is 0, mu of phi I minus 1 of Tk of Tj equals 0, okay? Because we have uncountably many of those guys. So in particular, the preimage of this guy, so in particular, these are continuity sets. Okay, because their boundaries are given by the these 2 points, and it is 0 in particular. Mu of boundary of Bij is 0. So Bij are continuity sets. Okay. And in these sets, phi is bounded above by Tj and below by Tj minus 1. Okay. So, and you can have that this Tj mu of Bij. So if you sum here with j equals 1 to k, so Tj is bigger than phi. Okay, in this, when you restrict to this. So this is greater than the integral of, so usually what I would have is the sum of Bij phi I d mu, which is the integral of phi I d mu, and it is bounded below, phi I is bounded below by Tj minus 1. So this is the sum Tj minus 1 mu of Bij. Oh, what did I do? There's no integral here. So this is j equals 1 to k. And by the choice of, choosing this so that it is less than epsilon, the step is less than epsilon here. So this is greater than the integral Tj mu of Bij minus epsilon, because Tj minus 1. Okay, sorry. Sorry, I think I'm getting a little bit tired with this abstract. Yeah. So similar, if you choose another nu in the neighborhood here, if you choose nu here, similarly, for nu in this Vc mu b epsilon, we will have the same equality with nu, which implies that the integral of phi I d mu minus the integral of phi I d nu, this guy will be less than the sum of L. So the t's are less than L, absolute value of mu of Bij minus nu of Bij, and then plus epsilon, this guy that you get here. So here you choose epsilon prime. Sorry, here it should have been epsilon prime. Epsilon prime is something that we're looking for. So choosing epsilon prime to be epsilon over 2kl. Sorry, here I should have chosen here epsilon over 2 to make everything works. Okay, epsilon over 2, because I will have here a term epsilon that I need to add with this. We get Vc mu b epsilon over 2kl So this is just abstract theorem, the portmanteau theorem, and yeah, I think there's time to. Yeah, let's quickly prove that this topology is metrizable before we close. So yeah, so this is abstract. So this is just a way to say that if you want to deal with this weak start topology, you can look at which one is easier among these four topologies we have: the continuity set, the closed sets, and the open sets. Okay, so 2.3, 2.1.3. I think I messed up with the notation. So the weak start topology is metrizable. This is useful in this existence theorem because at the end what we will do, we will prove that the space of probability measures is compact in this weak start topology. And for that, if we have the topology being metrizable, we just prove sequential compactness, like sequence has convergent subsequence. Like if any limit is in the set, yeah, so we will just prove sequential compactness. Okay, for that, let's define the metric here. Definition. So let D from, so this we define it in the space of probability measures. I don't know why I'm writing M, so I don't put the M inside because I know. So this is defined by D mi nu is the infimum of delta positive, such that mu of B is less than nu of B delta. Remember, B delta is a delta thickening of B. Like you take B, you add, you make it a little bit bigger by delta. That's B delta plus delta, and nu B is less than mu B delta plus delta. So this for all B in the Borel sigma algebra, okay? You see already this metric being defined using these sets make you think that it will be easier to use the topology with sets when we want to relate the topology given by this metric to the weak start topology. So a simple exercise is to check that this is a metric. D is a metric. Here all points are trivial except the triangle inequality. Like it is positive and the distance of a point to itself is 0 and it is symmetric by definition. So just check that you have the triangle inequality. Okay. So this is called, D is called the Levy-Prohorov metric. So D is called the Levy-Prohorov metric. So yeah, there is this proposition that tells you that the topology is metrizable, and this is a metric proposition. If M is a separable metric space, then the topology induced by the topology induced by the Levy-Pokhorov metric is equivalent to the Weak-Star topology. Yeah, probably if we do this, we're close for today. So let's go tau d, like the topology given by this metric. So we want to prove that tau d is equivalent to tau star. Okay? So the fact that tau d is stronger than tau star is trivial. So tau d is stronger than tau star. So to see this, you fix epsilon positive and F a collection of closed sets. So see that mu of Fi delta is converging to mu of Fi as delta goes to 0. So because this is this, you can write it as an intersection of these guys, and you have any theorem from measure theory that you can use to see this convergence. Okay, then so we fix epsilon, then so this implies that there exists some. So this implies that for delta small enough, if you choose delta positive small enough, you can have that mu of Fi delta is less than mu of Fi plus epsilon over 2, if you want. So small enough, probably, yeah, small enough. You know, this converges to this guy, so you can choose delta depending on this epsilon. And once you have this, you can check that if nu, so let's take the ball here. So let B D mu delta be the ball with respect to D, to the metric D. Okay. So what would you have here is that if you have nu here in BD mu delta, what does this mean? This means that mu of nu of Fi this is less than mu of fi delta, so it is actually strict, plus delta by definition of the metric. And this guy is less than mu of fi plus delta plus epsilon over 2 from there. And this is just telling you that if you choose delta less than epsilon over 2, you're good. So for delta in 0 epsilon over 2, we have b d mu delta is a subset of v, the topology given by the open sets f mu f epsilon. Okay, and this topology is the same as tau star. Okay. Okay, I have about 15 minutes. Okay, I can do it. Yeah, 15 minutes I think is good to have this second part. So now let's prove the reverse, which is tau star is stronger than tau d. So for that, what we do is we will prove that tau c is stronger than tau d, and use the portmanteau theorem, because this is equivalent to this. Okay. Yeah, this is the points where we need to use separable. So what do? We take here an open set here. So pick the open sets, they are balls. So let mu in M1, and then we need to, an epsilon positive. So this gives an open set BD mu epsilon. Now we want to find a neighborhood here. So we want to find epsilon prime and B, a collection of B1, Bn, such that Vc mu B epsilon prime is a subset of B D mu epsilon. Okay, so this is what we do. We have that this is separable. So we pick, let P1, Pn be a countable dense subset of M. Okay, we pick a countable dense subset. So see that for every R positive, you take this collection B, Pi, R. So now this is the ball on the metric on M. Okay, this is a point where we use also that the space is M is a metric space. Is a covering of M. So if M was compact at this stage, we would just choose a countable cover. But anyway, let's just stick to separable. I always use a separable here. But the thing is, we want to construct B of continuity sets. So that means that I want these guys to have like the how to say the measure of the boundary to be 0. So observe that for I fixed B, P, R, I, R, the boundary intersect with the boundary. These are spheres, okay? The sphere centers with different radius. They don't intersect, of course. Pi r prime equals empty for all r different from r prime. Okay, these are disjoint sets, so we can suppose that there is one r for which they all have measure 0, because otherwise you would have an infinite measure. Okay, so we're dealing here with finite measure. Then there exists are positive, small enough, you know. Really what I want to say is that if you fix any delta, for every delta positive, there exists R in this interval such that the measure of BPI R is 0 for all I equals 1 to n. Okay, natural number, right? So these sets are continuity sets of, and they cover the whole space here. So you can define, we fix delta that we will define how it is related to epsilon later, and also how R is related to delta. So here we have our delta. We take a set, let K be in N, a number such that this set U, which is the union of BI, R, I equals 1 to K, has a property that mu of U is almost 1, okay? No matter how small is delta, because this is a covering, so these sets, they have to go to 0 eventually, so you can stop at some point by reducing the measure of the space, 1 minus delta. If we had an open cover, we would not, if we had compactness, we would not need to put a delta here. We can just put a finite open cover for which this measure is exactly 1. Okay, so now with this collection, so let's say we have, let's call them by B1, BI equals, just a notation, BI R, okay? Now we have this collection of open sets. What I want to do now, I want to have a partition, let P be a partition of U such that if you have an element in P, then for every I will draw a picture for this. For every I in N, what do we have? We have either P is in BI or P intersect BI equals empty. So this is what you would have. So if you have this, these are your BIs which cover U. So you have U, what you do, you make a partition. The elements are these guys here. Okay? Sorry. So you take these guys like this. You take them so that either they are in BI or they. What I cannot do is I cannot take, for instance, if I come here, I cannot take this as a partition element. This is not good. Why? Because this set, it intersects this, but it's not inside. So you have to do it in this way. So these are the P's, okay? Yes. So observe that, and now let E be the collection. Oh, I forgot to say that P also will be continuity points of mu, because P, the boundary of P here is made of boundary of BIs, and the BIs are, so boundary of P is union of pieces of boundary of BIs, then PI, oh sorry, P, just P. PI is continuity point, continuity set. So mu of P, boundary of P is 0. So let E be the collection of finite union of partition element. Of partition element. Okay, I take finite union of partition element, and also see that elements of E are also continuity sets, because it is finite union, so their boundary will have 0 measure as well. So if nu is in VC mu E delta, then see that mu of E by definition minus nu of E is less than delta for all E. Okay. So in particular, so if nu is here, the measure of nu of U is bigger than 1 minus 2 delta, because the measure of nu will be bigger than the measure of, so let me write this like this. Mu of E, mu of U minus delta, which is bigger than 1 minus 2 delta. Okay. All right, so yeah, we are basically done here. So if we choose also, if we choose B is any, let B any continuity set of mu, so this B is a subset of M, okay? Any continuity set. So it will have a part that is in U and a part that is in U complement. So see that B will be a subset of EB union U complement, where EB here is the intersection of B with E, like the partition elements. So in some sense, you can write EB as P intersect with of B, sorry, B here. It's B like that. So choosing R, if you choose R small than small enough, you can guarantee that. So choosing, because R is the diameter of these guys. So if I make these guys small, choosing R small enough, I think here R less than delta over 3 is enough. We can make sure that EB is a subset of B delta. Like if you increase B a little bit, you will cover all the partition elements that intersect B. Okay? If you make R small, you make the partition element small. So in case you think of, you have your B, okay? Your B is like this. The partition elements, they are smaller ranges, so they do something like this, okay? I would draw also, they can be doing something like this. Something like this. But here, they don't exceed R here. They are in a R neighborhood of B. Okay, here also you have plenty of partition elements, okay? Sorry, this is not quite correct because, you know, B might not be covered by partition elements. You might just miss some parts, okay? So what this is saying is that if you make B a little bit bigger, you cover all the partition elements that intersect B. Okay? So what you have is now mu of B is strictly less than mu of EB plus delta. Which is less than nu of, by definition, by this, plus 2 delta, which is less than nu of B delta by this here, plus 2 delta, by the fact that R is chosen small so that this is a subset of this, so this measure is less than this. This inequality here, it comes from this here. And similarly, we have nu of B, which will be less than, here you go through mu and then go through nu. What you have now is plus 2 delta. And you go further, do the same thing. This is less than mu of EB plus 3 delta, and this is less than nu of B delta, mu of B delta plus 3 delta. So basically what you do is you choose epsilon that is smaller than, the 3 delta is smaller than epsilon. So choose delta. Says that delta smaller than 3 delta. Delta is smaller than epsilon over 3. So you choose R, which is of this size. Delta is of this size. And you would have nu will be in B, G, mu, epsilon. And you will have that this guy here, because any collection you take, you can write the B's, BI's, and do the same thing, and you would have that tau C is stronger than tau D. And this finishes the proof, because tau c is equivalent to tau star. Yeah. So I'm sorry, this is very abstract because it's an existence theorem, so just abstract results. And yeah, so what we will do this week, you will meet Mateos on Friday. I think there were a bunch of exercises from previous lectures. Next week we will finish this chapter. We will prove compactness, and then we prove the existence, and we go to the ergodic theorems. Okay, I stop here for today.